I want to review a few things that we've gone over so far to make sure that they are firm in your mind. And that is going to be related to forces at an angle, net forces and what that means, and this third law pair idea. We've been doing them directly and indirectly, but there's a couple important things that I want to make sure are strong in your head. First of all, when we do something at an angle, what does that mean as far as the forces go? What I'm asking by that is if I have a box and here I am going to push the box, and I have 3 legs. Let's make that a skirt then. And I'm going to push this box. If I push it straight on, that force applied, oops, let me make that clear, is all in the direction of the motion. So this box, theoretically, I push it hard enough, if there's friction or anything kind of resisting it, is going to slide that away. Now, if instead, here's my box, and make me bigger. Well, that's a long neck. If I am, say, pushing it down, so if my force applied is kind of going like that through the surface. So this would be, my picture's horrible, this would be something if you have a box and you're trying to move it across the floor, like if you ever moved, you got to move it across the floor, and generally what we do is the boxes are shorter than us, we lean down and our hands are at an angle. And when our hands are at an angle, we push on it. Well, that's what I'm trying to describe in this picture. As I'm pushing on it though, I have things that are happening. I have an X component of this force. Let's make that a different color so it stands out more. The X component of this force is the only thing in the direction of the motion. My Y component, so a piece of that force, is pushing it down into the ground. This X component in the direction of the motion, if this is where I would go, then is the force that is making it accelerate or just move at a constant rate if I have friction in the direction of the motion. So what happens when I push at an angle, not all of my effort goes into making it move. If I push straight on, all of that force is making it accelerate. At an angle, I have some of it that is pushing down. Like in this case, if there were friction there, then I'm increasing the force normal. Therefore, I'm increasing the amount of friction I'm trying to overcome. But the X component of that force is the only thing that's giving me acceleration in the direction of the motion. So at an angle then, 0 degrees gives me a force in the direction of the motion. In the direction of the motion. That is the optimal angle then. If I want all of my effort of motion, if I want all of my effort to go into moving or making something happen, that's the optimal force angle. The other one we can think about, you'll hear a lot, is if I do something at 45 degrees, that is like the optimal angle at an angle. We're going to actually talk about that. I'm going to leave that until projectile motion because we'll play with things to see what's happening with those vectors. What you can do on your own though is play around with what angle gives me the most force in the direction of the motion. That's an important part. So then the second thing here is this third law pair. Third law pair says that we have for every action an equal and opposite reaction. So one way to think about that is the old, here's my car, here's my windshield, and here's the little bug. That whole windshield and the bug thing. So the bug hits my windshield. My windshield is hitting the bug. They are experiencing the exact same amount of force. The only difference is from the perspective of the windshield, that force is no big deal. For the perspective of the bug, that's rather catastrophic. But that third law pair says that if the bug hits the windshield hits the bug with the exact same amount of force. That's your third law pair. So for a net force, I must have a net force, must have net to change my velocity, or change direction. And we'll see this one next week in lectures. That if I am going to say go around a corner, I have to have a net force. And that net force will be in the direction of the acceleration. So in our case right now, everything is rather linear. We're going at a straight line or up a hill. We're not turning yet. If I'm going up a hill and accelerating, the net force is pushing me up. If I'm not, if my velocity is not changing, then I have no net force. So if my change, that's what this little triangle means, my change in velocity equals 0, that means that the sum of my forces must equal 0. The sum of my forces must equal 0 if the change in velocity is 0 or the change in direction is 0. So straight line motion. That's a pretty important piece, because if you think in terms of anything moving, I think the biggest pitfall most students have when we first start off is you're like, well, it's moving, so there must be a force making it move. No, once I get it moving, I must have no net force to maintain that motion. I need a force or a net force in order to slow down or speed up. And one of the ways you can think about that is a car, right? You go at a constant speed on a flat road, then you have equal and opposite forces balancing that out. Your net force with respect to the car and the road is 0, as you're going at a constant speed. Keeping these things in mind, let's just do one small example before I do more complicated examples in the next video. This one is the third law pair example. And on this one, what we're going to think about in terms of equal and opposite reactions is that if I say push here, I push straight away. We won't worry about angles right now. I'm going to push straight on this little box. So here's little m, and this is big M, and this one is definitely more massive than the other. If I want to look at this in terms of forces, now remember in the last videos I said, well, we can treat this as a system, well, we certainly can. So I can say if I get this system accelerating, that the sum of my force push must equal mass 1 plus big M times acceleration. Sure. So the sum of my forces, actually let's call this in the X, is going to give me some sort of acceleration. No with friction, that means that I would have in my X, let's say I'd have like a force push minus the force of friction equals little mass plus big mass times acceleration. And that has me defining this away as positive. So let's think about this is treating this as a system. There are forces interacting between those two masses in that system. So I push here, I'm overcoming friction. Let's take a look at the free body diagram for this one. So for little m, what does that say? That says I have a force push. Let's do my free body here. I'll do it here. I have my force push going that way. There's my push. And in this one I said, okay, so I have friction. So if I'm accelerating, this friction is going to be smaller than the push. But I also have this box opposing my motion. So this box is pushing back on the little box. So remember, this dot is with respect to this little box. So that means I have, and I'm just going to do it down here so you can clearly see it, I also have a force normal of big M. So this, let me do a different color so it's not all blending. This here is what we would define as a force normal. So I have a force normal, and this is where it gets fun. I have a force normal also going up. This is force normal of little m on the Earth, and then coming down, I have a force of gravity. That vector made only larger, so it doesn't blend in with the normal from the other box. So if I wanted to do a summation of forces for my little box, in the x, let's see, I have, if I call this way positive, we'll stick with that. I have a force push minus the force of friction minus the force normal from m, or big M, let me be consistent there, pushing back on little m. And if this whole thing is accelerating, then I'm looking only at little m here, little m accelerating. Now, as you can imagine, we've done this for the system. One of the things that we can do is use this. If I know the strength of my force push, I can think of this in terms of my overall masses and acceleration. So these accelerations are still the same. That's nice. But students get to here and they're like, oh my goodness, this is ugly. I have 3 terms. What am I solving for? And that would depend on what I was giving you. And here's what I always tell people. Don't start with this thing. It's okay to start with this thing, but that doesn't tell us anything about this normal. If I start here, that gives me acceleration. That's handy. If I start here, like that's lots of terms. But let's think about the big M free body diagram. What does that have? Well, let's see. It has a force normal from that little m going that way. So force normal from little m pushing on it. This one I made have friction, so it's got friction opposing it. And then the standard force of gravity straight down towards the center of the Earth, and force normal perpendicular to the surface. It's a flat surface, so it's straight up. So my summation of forces here gets a lot prettier. That says that I have, if I go this away is positive, that says I have a force normal from little m minus the force of friction equals big M times A. Now here's where I can kind of deduce and use the third law of pair to my advantage, because this force normal, well, that is going to be the same. However hard this little mass pushes on the big mass is pushing back on the little mass by the same amount. Let me repeat that. However hard the little mass pushes on the big mass pushes back on the little mass by the same amount. So that means that my force normal for the little mass equals the force normal for the big mass. So this is the contact force between the two. So for this one, I could solve, right? I could put the force normal between the two equals these two quantities. And I could put that in here. That's no problem. And then I'd rearrange and move my mass times acceleration over the other side. It's a little mathematically ugly, but when you start putting some numbers in there, like if I know the size of my force push, okay, I can solve for that. If I know the masses of the two things, I can solve for the force of friction, because that's just going to be, if I'm moving, the normal times the coefficient of kinetic friction if it's in motion. So I can solve for that. That's straightforward. And relating these two things, then I can figure out what the normal is between those two boxes. So on your quiz question this week, what you get to consider is, what is the normal between these two if I push from this side? And what is the normal between these two if I push from this side? That'll be a fun one to chew on. Think about it.